All right. Hello, everyone, and welcome to this week's Tech Talk. Uh, the Library Data Hub's Tech Talk series is all about connecting U of I community members with tools and discussing topics that can help them do scholarship and research in this sort of digital and information age. To that end, today, we have Luke Sheneman, the Director of Research Computing and Data Services, who is going to talk to us about CUDA. CUDA? How does one CUDA? How it can be used for computation on GPUs. So go for it, Luke.
Okay, great. Thanks. Good to be here. I'm going to go ahead and share my screen. And then we'll just go ahead and... Okay. Can you see everything on Zoom okay? Okay. And then you can hear me on Zoom?
Yeah.
Okay. All right, here we go. Yeah, so my name is Luke Sheneman. I'm the Director of Research Computing and Data Services. We're part of the Institute for Interdisciplinary Data Sciences here at the U of I. We provide sort of the majority of the research computing infrastructure, like high performance computing, GPU nodes, storage, things like that. My team also manages the Falcon supercomputer. And we do a lot with web application and mobile application development, database development, that sort of thing too. So RCDS is our name, and be happy to talk to you after if you've got any questions about that. But today I'm going to be talking about doing accelerated computing with CUDA, which is something I've always wanted to learn more about. And so giving this presentation was a good excuse to sort of dive in myself. So why am I giving this talk? I wanted to kind of demystify the use of GPUs or graphics processing units for general purpose accelerated computing. So not so much for doing graphics, which is what they were originally invented for, but for doing science and research and other kinds of compute intensive things. I want to demonstrate to everybody who hasn't worked with CUDA directly how easy it is to get started. But then how that rapidly becomes kind of hard, and then show you some ways that it can actually be kind of easy after that, and give you some basic code. So give you kind of a head start, like if you've never played with CUDA, like how do you even get going? How do you start programming GPUs to do things? So give you a little bit of code to get started. But there's a lot of science is done on GPUs, an enormous amount, right? So I think increasingly we're finding that researchers are leveraging the power of parallel processing capabilities of GPUs to do all sorts of analytics, right? Whether it's, it was applied in a lot of ways that's shown on the top graph. When COVID-19 sort of hit the scene, GPUs were used in a variety of the different parts of that epidemic, to help understand the virus, to help build tools and drugs to fight it. And I love this picture below of Katie Bowman, who was the scientist who was the first person to ever image an actual black hole, and using terabytes and terabytes, actually petabytes of data. And GPUs were a critical part of that analytical pipeline. They just wouldn't have been able to process the data fast enough without GPUs. And so accelerated computing, going beyond just the use of sort of traditional central processing units of CPUs, I think is really exciting. So today's like the CUDA coaster, right? Because like I said, I'm going to kind of show you how easy it is to do like a hello world kind of thing in CUDA. And then quickly that is going to break apart, and you're going to see how hard it is to make actually really good, portable, optimized, fast CUDA code that like makes the most use of a GPU. But then I'm going to turn that around and show you how trivial it actually is with some of the libraries that are available to use CUDA in your science. So this is obviously an AI generated image of a GPU coaster. So, and like the horror that these geeks are feeling. So GPUs were invented for 3D graphics, right? So way back when. And the reason why is because 3D graphics is done almost entirely with linear algebra, right? It's a bunch of vector and matrix multiplications to do things like translation, scaling, rotation, perspective projections. All those things are actually mostly matrix multiplication, right? Uh, and having just a central processing unit be responsible for doing all of that, it was just too slow to be able to generate, for example, 30 frames per second in a video game or in an animation or whatever. And so that's where GPUs came along. That's why they were invented. But today you're seeing this idea of accelerated computing take hold. It's been around for a while now, but it's increasingly becoming important. And the idea behind accelerated computing is it's this computational approach that uses specialized processors like GPUs in conjunction with traditional CPUs to get dramatic computational speedups. And so what you're seeing in this picture here is the Aurora supercomputer that, you know, is has been built, has been installed, and it's still, I think they're still bringing it completely up online at Argonne National Lab. So this is the fastest supercomputer once it's fully operational at 2 exaflops of performance. It's a huge data center, 166 racks, 10,000 individual blades. This blade, I'm showing a blade right here in this other picture. On that blade are 2 CPUs and 6 GPUs, right? So there's way more GPUs on Aurora than there are CPUs. And it's all Intel. So it's an Intel CPUs and Intel GPUs in these blades, and there's 10,000 of them. So it's this enormous machine built with GPUs in mind to help accelerate computing. And you're seeing more and more of that. So if you look at the top 3 fastest supercomputers, you see Frontier, Aurora, and Eagle. I think Aurora is number 2 only because it's not fully up to speed yet. It's still installing it. But all 3 of the top 3 supercomputers all have GPUs. And they have from different vendors. So Frontier uses AMD GPUs, Aurora uses Intel, and Eagle uses NVIDIA. Right. So GPUs are increasingly being used in all of the supercomputing applications, but obviously GPUs aren't just in supercomputers. They're actually in all sorts of things. They're in servers, desktops, workstations, laptops have GPUs, tablets, smartphones, embedded devices. My iPhone has GPU cores in it, right? Like it's crazy. GPUs are just everywhere now. And what's that?
Are they energy efficient as well as speed efficient?
I'll get to that in a minute. In general, I think you're able to do more computations with far less power with a GPU than with a CPU, but there's some nuance there. Yeah. In Google, some of the big hyperscalers like Google and Amazon and others are actually working really hard to build their own silicon. Tesla is another one, building their own chips to do this sort of accelerated computing. They're like GPUs, but specifically for artificial intelligence and accelerated computing workflows. Okay, so there's all sorts of GPU programming platforms out there. CUDA is only one of them. And I kind of grouped them here in proprietary versus open source. So the proprietary ones are CUDA and then Apple's Metal API, right? So Apple has their own GPUs that are sort of built into their systems, and it's called their framework is called Metal. Then there's a whole bunch of open source ones. So the GPUs for AMD, for example, use something called ROCm. Intel uses something called OneAPI. Vulkan is supposed to be a system that will work across multiple different types of GPUs, as well as ZLUDA, which I only recently learned about, which is intended to provide the CUDA API, but for other vendors' cards. So specifically for AMD, originally also for Intel, but there was some lawsuit, and now it's just for AMD. So there's a whole bunch of open source attempts to do this, and AMD and Intel are like going full bore on the open source side, thinking that eventually that's going to get them to a better place than the proprietary frameworks. But why? Okay, so why do we focus on CUDA? Well, if you look at the distribution of who's using CUDA versus or NVIDIA versus the other GPUs, it's like a year ago it was like 98% NVIDIA in data center GPUs. Like they almost have a monopoly, right? AMD is starting to eat into that. Intel is starting to eat into that, but still, it's by far kind of the lion's share. And so, all of the major software systems, the AI deep learning frameworks like TensorFlow and PyTorch all use CUDA really, really well. They've been well tested on it. They can also use some of these other platforms like ROCm, but Anecdotally, I think it works, it tends to work way better on CUDA just reliably in production than it does on these other platforms. The CEO of NVIDIA, Jensen Huang, he's famous for saying it just works. That's one of the reasons why you want to use NVIDIA and CUDA is it just works. And there's actually, if you follow this YouTube video, there's actually this 10-hour video of him saying it just works in all of his presentations over the last couple decades, like 10 hours of him just saying it. So he's obviously famous for saying it, but it is somewhat true. And that's why these are being adopted. Okay, so what is CUDA when I say CUDA? So CUDA originally was an acronym that stood for Compute Unified Device Architecture. I think most people just call it CUDA now. They don't really break it up into that acronym anymore. It was originally released a long time ago, right? 2007, right? And it's not just an API, and it's not just a bunch of libraries or drivers. It's like a whole platform. It is actually language, right? So it is an extension to C and C++, but also Fortran. It is a set of APIs to help manage and control devices. It's a set of development tools like compilers, debuggers, and profilers that, it's this full-fledged, developer stack for coding and writing code for various applications and workflows. But it's also a collection of libraries. So there's this huge collection of libraries that is growing that people use for all sorts of things. So there's cuBLAS, which is, I think BLAS stands for Basic Linear Algebra Subroutines. It's matrix multiplication, vector addition, those kinds of dot products, things like that are implemented in a very efficient way. And so you don't have to implement them in a low level. You can just import this library and go to town, doing matrix multiplication in sort of an optimal way. Fast Fourier transforms, various solvers for doing ordinary differential equations, where for the kinds of ODEs that this can apply. Things for random number generators, basic accelerated math. Thrust C++ just has a bunch of GPU accelerated algorithms like sort, like sorting, where it actually use GPUs to make that really fast. Things like that. So these libraries are all freely available when you use CUDA. Okay, but really importantly, like if you're actually going to program in CUDA, you have to understand the hardware. It's really important. So I'm going to talk a bit about that. So first of all, what's the difference between a CPU and a GPU? Okay, so a CPU typically has a small number of cores. So here, a core is like a unit of, it's a unit of computing. And I'll break down a core in a minute. But in this particular case on the left, you see a CPU that maybe has 16 cores, which, that's still kind of that's a moderate size, computer these days. But they're good for heavy tasks, right? Where you have lots of instructions, you've got all sorts of diversity in your data and your branching routines and things like that. It's good for that sort of common computation. A GPU, on the other hand, has a huge amount of cores. I'm talking about thousands or tens of thousands of cores per GPU, but they're really kind of dumb cores. They're really good for doing very simple, lightweight tasks, but there's a bunch of them, right? And they're optimization specifically for doing graphics computations. Looking a little bit deeper on the left-hand side, you can see, a typical sort of layout of cores and memory. And that's really important. Like not only how many cores a system has, but then what's the memory hierarchy for that architecture. So on the left, you see a 4-core CPU. That's each core has associated with it L1 cache. So cache is just a small amount of memory that is really, really fast, but only that core each core can access its own L1 cache, right? But it's really fast. But if one core needs to talk to another core, they can't share the same cache, right? So you have L2 cache where multiple cores on the same socket can share memory pretty fast. You have level 3 cache, and then you have your main memory. So that's a CPU. On the right-hand side, and by the way, that is an example of what they call either single instruction, single data, which would be like a 1-core system, or multiple instruction, multiple data, which is a multi-core system, or and then on the right, you have a GPU, which, as you can see, is laid out very differently, right? It's in this grid of cores. A whole bunch of cores have access to the same shared cache. And then that's an example of what they call single instruction, multiple threads, or single instruction, multiple data. So one instruction can execute across multiple cores at the same time. And so we'll talk a lot more detail there. So that when you're talking about the hardware, there's really kind of three things that you need to look at, right? There's the physical hardware, so how many CUDA cores it has. There are these special parts of a GPU called streaming multiprocessors, or SMs. And then there's memory controllers. We'll talk a lot about the cores and the streaming multiprocessors, but not so much about the memory controllers, although we will talk about the importance of memory. And then there's the memory hierarchy, right? So there's the global memory. So the global memory on a GPU is sort of the memory that every core has access to, right? It's kind of slower than some of the cache memory and things like that, but that's if you load some data onto a GPU, it's probably going to end up in the global memory by default. Then there's what's called shared memory, and the shared memory is memory that's shared by a subset of the hardware at any given time. And I think the shared memory is associated, I believe, with each streaming multiprocessor. And then you've got level 1 and level 2 cache. And then at the smallest granularity, you have what are called registers, which are just things that can hold single variables or some small number of variables that can be used inside of loops and things like that. For, each core has access to some number of these really fast registers for that kind of code. Then you have your instruction execution. Okay, so how do you actually execute instructions on your GPU? And these are low-level, like, machine instructions. You have to understand that things are broken up into what they call thread blocks and grids, and I'll talk about that. You have to understand this idea of warp execution, and again, I'll get into that, and thread scheduling. So let's look at an individual CUDA core real quick, okay? First of all, before I get into what the parts of the CUDA core are, you should understand what we're talking about as far as how many cores these GPUs have. So an A100, an NVIDIA A100, which is one of the kind of the workhorse GPUs out there, has about almost 7,000 cores, okay? An H100, which is the newer version that is out now, and we just bought 3 of them. I'm really excited. Has about 15,000 cores, right? So that's great. That's how many cores that they have compared to, again, CPUs that might have 16, 32 at the most. Some of them have 128, but we're talking tens of thousands of cores. Commodity desktop GPUs actually can have quite a few CUDA cores. And so like a GeForce RTX 3090 has 10,000 CUDA cores. A 4090 actually has more than an H100. It has 16,000 cores. But these cores, like I said before, are simple, dumb, and kind of slow actually compared to a CPU core. But there's so many of them, and you can run them all at the same time. Getting to your point about power, and cores. So 2 of these H100s GPUs, just 2 of them, has more cores than this 14, 15 rack supercomputer that we run at INL, right? So we have about 15,000 for about 32,000 cores for 2 H100s and about 30,000 cores across a whole bunch of servers at Falcon, right? Now the cores aren't the same thing. A CPU core is not the same thing as a GPU core, but still, I wanted to give you that point. And so for certain workflows, it is way more power efficient to use a GPU than to use a CPU. 2 H100s consumes 1.4 kilowatts at peak use, and Falcon will use 350 kilowatts, right? So orders of magnitude more power consumption if you don't use a GPU for certain workflows. So a CUDA core has these parts. The big thing to realize is that, instructions come in, operands, basically operands for these instructions, like if you're doing an addition or a bit shift or something like that, those come in and they're handled by either a floating point unit or an integer unit, and you have like a results queue. It's sort of traditional sort of computer architecture, but it's relatively simple. There's not a lot of bells and whistles. These cores are kind of, like I said, kind of slow, dumb, and simple. Okay, so a streaming multiprocessor. I talked about this before. So the streaming multiprocessor, you can see on the right here, is composed of some number of these CUDA cores. And the streaming multiprocessor is kind of like a control system within the GPU that controls the execution of instructions on various cores, okay? It does things like schedule when threads get run, or it controls the memory management so that things are sort of optimally aligned in memory and accessed in memory and that sort of thing. It does load balancing across cores and across other streaming multiprocessors. So it's kind of a little brain that does scheduling. You can kind of think of it that way. An NVIDIA A100 has 108 of these streaming multiprocessors, and H100 has 144. The B100, which was recently announced, we think will have about 192 of these streaming multiprocessors. So they're getting more and more of these over time. So getting back to the memory hierarchy, if you look on the left here, you can see each one of these is a streaming multiprocessor. And each one of those has its own cache, own level 1 cache. And it's relatively small. You're talking about 100. It looks like, for this particular example, it's like 192 kilobytes, right? It's a really small cache for that particular streaming multiprocessor. Then they have access to level 2 cache, which is shared across the streaming multiprocessors, and then that's faster than global memory, but much smaller. And then you could have global memory, which might be 40 gigs in an A100 or 80 gigs. And these the memory is important because when you're actually executing instructions on the GPU, you have to understand that global memory is slow but big, and shared memory or some of these fine-grained cache that are more closely aligned to a particular streaming multiprocessor, those may be much faster but much smaller. And so from a thread standpoint, and I'll talk about this in a lot more detail, you take your GPU and you create a grid out of it. And the grid is basically a bunch of what they call thread blocks. And those thread blocks execute within particular streaming multiprocessors, and they have access to, all of them have access to the global memory, but then they have limited access again to shared memory, et cetera. And so, what are the memory types? Again, there's a whole bunch of them: register, shared, level 1 cache, level 2 cache, global memory, constant memory, and texture memory. The texture memory is like a holdover from graphic stuff, where it can actually hold textures that you're gonna apply when you're texturing a scene or an object in a scene. But what we're going to talk about and why they're highlighted in red are pretty much exclusively is global memory, which is the largest and slowest type of GPU memory, accessible by all of the streaming multiprocessors, and the shared memory, which is located within each streaming multiprocessor, and it's accessible by all threads within a block. So any thread within a block, and again, I'll go into that because that's super important. But it's fast, right? And so those are kind of the two that you mainly have control over, and that's why we're going to talk about it. Okay. So we talked about memory, we talked about cores. Now let's talk about the thread execution hierarchy, right? So this is how things get actually executed on the GPU. There's like this nesting thing. The thread is the lowest level of execution, right? So a thread is just it's basically a unit of execution on the GPU. Threads are organized into things called warps. And a warp on an NVIDIA GPU across all their models is 32 threads. So a warp is 32 threads. And a warp, the term warp actually comes from weaving. And so if you look here, these white strands that are sort of vertical here in this picture are called warps or warp threads, and then you wrap your other threads around them. That's where the word comes from, not warp speed from Star Trek. But anyway, then those threads and warps are what are inside things called blocks or thread blocks, and those then are inside of a grid. So the grid is it can exist across the entire GPU, across all of the streaming multiprocessors. And then within that, you have blocks. And within blocks, you have warps. And within warps, you have threads. Okay. Yeah. So I kind of just went over this. The idea that a thread can kind of execute on an individual CUDA core. A CUDA core can execute multiple threads at a time concurrently. it has that ability, but you can just think of it as like a thread to core kind of correspondence. A thread block requires a streaming multiprocessor, and an entire CUDA grid associated with a particular kernel, and I'll define that in a minute, composed of multiple streaming multiprocessors. Okay. So again, threads are the smallest unit of execution. Each thread on your GPU, at least within your kernel, and again, I'll define that in a minute, has a unique identifier, right? So you can actually address every thread. Threads are organized into warps, and a warp is 32 threads. And the thing is that a warp can execute one instruction at a time, okay? So that means that if you have 32 threads in your warp, you can only execute one instruction at a time. And so you better hope that all 32 of your threads you want them to execute the same instruction, right? Because that way you'll have more optimal code. And I'll talk about what's called thread diversion warp diversion in a second. So blocks are groups of warps. Oh, by the way, I should mention that warps, even though threads are uniquely identifiable, like you can address threads individually. In CUDA, you can't address warps. There's no addressing for warps. So you can kind of infer where a warp boundary begins and ends based on how you do the math, but you don't address warps specifically. Blocks or thread blocks are groups of warps, and it's a unit of execution scheduled by the CUDA runtime. A block can be either one-dimensional, like a vector. It can be a two-dimensional block, or it can be a three-dimensional block. It really depends on the kind of math or the kind of graphics that you're doing. And each block has fast shared memory, and the threads within a block can be synchronized. So normally when you're executing the threads inside of a block, they can execute asynchronously, right? They can kind of do their thing, but you can force them to synchronize at various points. And a block itself cannot span multiple streaming multiprocessors. And then finally, you have a grid, and a grid is kind of the highest hierarchy, right? And it consists of these blocks. And again, the grid is also like your blocks. It's either 1, 2, or 3-dimensional. So here's an example of a CUDA grid, okay? And this is a 2-dimensional CUDA grid that is defined for a particular, what they call kernel. This grid is allocated for that kernel. And that grid is comprised of these blocks. In this case, what's there? 9 blocks, and each block has a dimension of 9 itself, right? And it's 2-dimensional. So you can identify each thread in here by its address, but you have to identify first what its block ID is, and then from there to the thread, right? So this is a super simplistic version, but that's a CUDA grid, and that's really important because every kernel is associated with a grid. A GPU can run multiple kernels, each with their own grid on a GPU at the same time, which means they're just using different parts of the hardware, different CUDA cores under different streaming multiprocessors. But we're going to just do one grid at a time here. Okay, so I've mentioned this idea of a kernel a bunch of times, right? So a kernel is where you come in. A kernel is what you code in CUDA to execute on the GPU, okay? And like I said before, a CUDA kernel that you define is associated with a grid that you allocate, and then you launch your kernel. They call it launching the kernel. You launch it onto the GPU, and it executes. And that's sort of the CUDA programming model. Okay, so let's make a super trivial program in CUDA, okay? So this is adding 2 + 2 on a GPU, right? I hope you guys can see this, but up here, you can see it looks a lot like C code because it really is C code. It's like an extension to C or C++. But you define your kernel with this __ global __, and then you define sort of your function, which is your kernel. In this case, we're taking a pointer to an integer, which is one of the things you're going to sum. another pointer to another integer, and then a pointer to where you want the result to be placed. Okay. And then inside the kernel, you're literally just adding them, right? And that's it. So that's a complete definition of a CUDA kernel. This will execute on a grid, and it will execute on a, under one streaming multiprocessor on a GPU. So in the main function, I'm going to do this, right? I'm going to declare A, B, and the result as integers. I'm going to set A and B equal to 2 because I'm going to do 2 plus 2. Then I create pointers and if you don't remember C code, this asterisk character signifies a pointer, right? It's a memory location for that variable. So I'm going to create a pointer for the DA, which is the device version of that variable, device meaning GPU, the device version of the B variable, and the device version of the result, okay? And then I call this thing called CUDA malloc. So what I have to do is allocate on the GPU memory to store those integers, okay? A, B, and the result. Did you have a question? Oh, okay, sorry. And then what I do, so once I've allocated those, then I copy my actual variables A and B, the ones that I've defined to equal 2. I copy those to the GPU with this CUDA, with this CUDA memcopy command. And there's this extra, so I give it the pointer to where it is in on the device. I give the pointer to the actual value here, the variable that has the value 2 for A. In C, if you recall, it's not aware of the size of your data. You have to always tell it. So we say size of int, which is the number of bytes of an integer. And then you have to give it this thing, which is this little flag that says CUDA mem copy host to device. So I'm copying my variable from the host to the device. I do that for A and B. And gosh darn it. And here is where I actually launch the kernel. Okay. If you see, I'm calling add, which was the routine that I defined up here. I defined my kernel here, but I'm launching it here. And I launch it by, first of all, with these kind of triple chevron things. And the first thing is your, I think it's your block size. And the next thing is the number of threads you want to allocate. So I'm saying I want to allocate one block of one thread, right? Because that's all I need to calculate 2 by 2 or 2 plus 2. And then I pass the arguments, the pointers to the device memory. And then when that's done, I have a result, but I have to copy it back. The result is actually stored on the GPU. I have to copy it back using CUDA memcopy from the device back to the host, and I get a result. And then you can free the memory that you allocated. So, I mean, come on, that's in one sense easy. In one sense, for adding 2 plus 2, that's kind of hard. But, this is a kind of a toy example. You would never actually do this because adding 2 plus 2 on a GPU is going to take way more time because you got to move the memory and allocate the memory. But anyway, this is how you create a kernel and launch the kernel, and that's pretty much it. Yeah.
Function called CUDA malloc
Uh-huh.
Just keep this CUDA memcopy because
yeah, right.
what's the difference between CUDA malloc and
Yeah, so there's a way, I think what you're talking about is like virtual memory. You can create a virtual memory framework where you're basically creating a unified memory system where it's basically a layer of abstraction where you don't have to do these explicit mem copies, that it's kind of shared between the GPU and the host, and the compiler kind of knows the difference. Yeah, and so I'm not going to talk about that today, but you're right. There is a unified memory method using what they call virtual memory that you can use. And yeah, that's a good point. It's the same thing. It's just, it kind of hides the details a little bit, but under the hood, I think it's doing the same thing for you. And the compiler is doing that for you. Okay, so here's the CUDA steps, and we just went through this, right? And I'll kind of go through this code again real quick. So you define the kernel function, you allocate memory on the device for your variables. You copy. So a lot of what you do in your code, in your in your CUDA code when you're not in your kernel is allocating memory and copying things back and forth between what they call the host, which is your CPU, to your device, which is your GPU. And then you launch the kernel, and then you copy the result back and you free it. And that's pretty much it. And so if you look over here on the left, you can see you can have multiple kernels, concurrent kernels running at the same time. Here I've got kernel 1 on the host that is copying and executing things on a grid over here, and then I have another kernel down here that's doing the same thing at the same time on different streaming multiprocessors. And you could take full advantage of all the CUDA cores by having what they call full occupancy of the GPU, by having it fully busy doing things. Okay, so now let's talk about what's often considered kind of the hello world example, which is vector addition, right? So vector addition is really easy. You have, and again, this is where CUDA really shines, is linear algebra. So here you've got a vector A, which is, the values 1, 2, and 3, and the vector B that has 4, 5, and 6. And to add them, you literally add the value from each position together. So A0 plus B0 equals 5 in this case, and et cetera. So it's pretty straightforward. On a CPU, this is an order in complexity, right? If the single thread, you've got to go through the vector one by one and add them all together. And so it scales with the length of your vector. If you had a vector that was 5 billion values long, your one CPU thread would have to go through each one of them individually, and it would take a long time. But in theory, you could do it in 1 or 2 clock cycles on a GPU, right? And so this is how you would define the kernel for that, right? Again, you have to, when you launch, I'll get into the kernel launch real quick. So first of all, I'm going to define a block size of 256. I'm going to define a grid size, and the grid size is basically how many blocks are going to be in this, and it's going to depend on the size n, which is the length of your vector, right? So you define your grid size and your block size, and those are what you pass to in those triple chevrons when you call your kernel, right? You have to tell it how big your grid is and how big your blocks are, and it's going to depend on the size of your data, right? So you have to keep that in mind. And so then inside the kernel definition, we didn't have to do this for the 2+2 example, but inside the kernel definition, now we actually have to find our thread ID, right? And our thread ID can be found, and this is pretty much boilerplate for most CUDA kernels, right? Is you have to find your thread ID. In this case, we're finding the block ID index. We multiply that by the block dimension, which, is, which is the, in our case, it's 256. And then we add to that our current thread ID, which these are built-in values. Block IDX.x, block dim.x, and thread IDX.x are built into CUDA, and they're just there available for you to use to index your threads in your CUDA code. And so then I just have this conditional that, as long as we're less than the size of our vector, we just add, C thread ID equals A thread ID plus B thread ID, okay? These kernel will execute across lots of cores simultaneously, right? In theory, all of them all at once, and be done immediately. So again, you could do, if you did this with a CPU or one thread, it would take you n steps with one thread, but with if you have n threads, you can do it all in just one step, right? So it's super fast. So that's a really good sort of hello world example. Matrix multiplication is similar. Matrix multiplication gives you an example of what it might look like to do this in multiple dimensions, right? So in this case, you have a rows and columns, and you have block ID Y and block ID X. And so that's how you find in your two-dimensional blocks your thread IDs, right? But it's the same kind of thing. You can find your rows and columns, and then you can do the math, which is shown here on the right on this little animated GIF. Those are the steps required to do matrix multiplication, which is, by the way, the most common GPU function, right? Is matrix multiplication. But that's the CUDA kernel to do that. And we launched the CUDA kernel in a very similar way. Now, you'll see that there is another data type in CUDA that's defined as dim3. We didn't have to do this for our 2+2 example because our grid was a vector. It was just one dimensional. But now we have a two-dimensional grid with a two-dimensional thread blocks in it. So you have to define that is actually two-dimensional. You have to give it the two dimensions. I could also have put a third dimension here if I was defining this as a three-dimensional grid or a three-dimensional block. So you define your blocks and your grids, and that's what you pass in these triple chevrons to your matrix multiplication. So, and again, DIM3 is a native CUDA data type. Dot products, similar thing. So a dot product is where you take two vectors, you apply the dot product, you get back a scalar value, which is a simple value, which will tell you the angle between them, basically. This is what's used for, an infinite number of times every time you use ChatGPT, right? It's dot products. This is how they compare the embedding vectors for two tokens when they're doing self-attention in transformers, is they're computing dot products. So this function is probably now surpassed matrix multiplication as the most important function for GPUs. You'll see that there's a couple things in here that I wanted to highlight in the kernel. One is that I'm declaring an array of size n in the shared memory. Shared memory, if you recall, is local to this streaming multiprocessor, or to at least to this kernel, wherever this kernel is running in that streaming multiprocessor, and it is fast. So things that are read or written from that memory is way faster than writing to global. So if you've got some scratch space that you need to work on inside your kernel, it's better to do that in shared memory. It's way faster. The other thing that we do here is there's this call to sync threads. So what this means is this will synchronize all of the threads that are currently executing in that block. It will make sure that they all complete. Because what ends up happening in this, you'll see that the result of the dot product is actually stored in the 0th position, or the thread that has the 0th index. It gets stored there, and then returned. And so before you can do that final summing step, you've got to make sure that all of your threads have finished executing. They've done all of the other steps that they need to do before you do that final sum. And so these examples are actually, relatively simple. And I think once you start coding them, you get the hang of it, not pretty fast. But these sort of assume that these computations, that your memory can all fit within, within your GPU, within your particular grid and block size. Once your data is bigger than that, you have to handle that situation explicitly, right? You've got to deal with that. I wanted to give you kind of a harder case, which is summing a vector. Okay, so when you're summing a vector, if you're just going to go across the vector and you just want to add up all the values, say come up with a single scalar value, which is the sum of all the values in the vector, normally that's an order in operation, right? You've got to go through each one of them to do that if it was a single thread. The naive approach would be to basically set up your threads so that basically one of the threads is accessing the data from its neighboring thread and summing it. And you do that sort of, all the even numbered threads are basically summing from its neighboring odd numbered thread. You sum that together, you change your stride. You double your stride from 2 to 4. You do it again. You double your stride to 8, and you do it again, et cetera. And that's great. And you can see that it comes back to a value that is the sum of the original vector, and it does it pretty quickly. But the problem with this is that in order to do this, it requires some conditionals in your kernel, and those conditionals will cause it so that remember, threads have to execute in units of warps, and so you can see that a lot of these threads in here aren't doing anything, and some are. And increasingly, some of them are just idle. But it turns out that after a while, because of the conditional, some of your threads are active and some aren't. And the ones that aren't are basically failing some if condition inside your kernel, which means the whole thing has to wait for that to fail before now doing the next thing. So you have to be aware of the fact that these threads execute together in a warp. And otherwise, you end up with what's called warp divergence. So threads within a warp that end up doing different things at different times. And that happens, again, because of conditional branches in kernels. Yeah, I didn't look at that example in the case of trying to understand the thread divergence or the warp divergence in there. But yeah, you might have a similar problem with doing. Yeah, right. And you're probably right that there would be a similar kind of thing, except the result there though is itself a vector, right? And so each of the threads could just execute simultaneously. You're not dependent. There's no stepwise dependency, right, on the vector addition. On the dot product, there would be though. You're right. So yeah, I didn't look at it from a warp divergence situation. So the trick is you have to think long and hard, like, okay, am I actually optimally using all of the threads in my warp optimally? Are they all doing the same thing in lockstep like I want them to do? And often all that does is require some rethinking of how you structure your code so that if there is the need to do conditionals, that maybe you separate that or structure your code so that warps tend to be able to all run the same code at the same time. And so, the other thing is bank conflict. So that's another thing to be worried about, right? So a bank conflict is where threads try to access the same shared memory. This only really applies to shared memory, but they try to access the same bank in the shared memory, but they're looking at different values. So shared memory is organized into these small banks of, I think, 4 or 8 bytes or something. And so if you're using small data types, it could be that like 2 threads are trying to access different parts of memory in the same bank. And if that happens, they have to wait. Okay. And they have to wait for that access. So they have to start serializing their access to those banks. So bank conflicts are another issue. So we're definitely in the like horror part of the GPUs, right? Okay, so and there's a way more complicated things that you like a professional CUDA programmer would have to deal with if they were trying to make truly optimized code in CUDA, dealing with just resource management, memory management, making sure that you're optimally using all the cores that you can, that you're moving data efficiently, that you're using all the shared memory. It's tricky to do it right. So how do I start writing CUDA code? Okay, well, the first thing is that you have an NVIDIA GPU installed. CUDA only works on NVIDIA GPUs. I believe it works on all of them at this point, at least everything since 2007. I think there's, you can get some version of CUDA running on all of them. You have to have your NVIDIA drivers on there. So hopefully you do. That's pretty straightforward. And then you have to install what's called the CUDA toolkit. So the toolkit includes things like the compiler, the runtime, some utilities that help you like monitor your GPU, that sort of thing. NVIDIA's got documentation on how to install this across most of the different flavors of Linux and Windows. And it's actually pretty straightforward. It's not too hard to do. But and you can do this also on Google Colab. There are ways that you can get access to do direct CUDA programming in Google Colab. Put a link here. I'll share my slides in my GitHub later, but if you follow that link, there's instructions on how to do this in Google Colab, so you can start messing around with this. But one of the commands that you get, at least in Linux, once this is installed, is this NVCC. That's the compiler, right? That's the CUDA compiler, and it works just like a C compiler. But if you do NVCC-V, it'll tell you the version, and you know that you've got CUDA installed and ready to go. So that's not that hard, I find. If you need access to resources to develop and compile and run CUDA code, we've got tons of GPUs at RCDS that you can have access to. Just make sure that you reach out to me. One of the best ways, if you can schedule your CUDA jobs across our GPU nodes pretty easily. But one of the best ways to do it, and I know Bruce has been doing this, not for CUDA programming, but for using GPUs with applications, is to use the on-demand interactive interfaces. So this will actually give you a shell on the device. You don't have to run it through our normal sort of job scheduler, and you can just interactively compile things and run it and see how it's utilizing GPU resources. Okay, so I went through the horror part and kind of defined like how to actually code stuff in CUDA itself. But you can also do a lot of CUDA programming just right in Python, right? Where it's still incredibly efficient. There's a thing called PyCUDA. There's actually a number of these sort of wrappers around CUDA in Python, but PyCUDA is maybe the most popular one. And it's kind of cheesy, really, what it does. What it does is it allows you to define a CUDA kernel in C code or in CUDA C as a string and then deal with it, right? So you're still writing at least your kernel in C. But then the memory management, the allocation, all of that stuff is actually just in Python. And I'll show you examples here in a second. Triton is another system that you should really take a look at. This looks incredibly powerful. So I haven't messed with it that much, but it's was made from a developer at OpenAI. It was released a couple of years ago. It's a Python-like language. It looks just like Python. In fact, you can use most Python libraries with it just fine, not in your kernels, but in sort of the supporting code. It's the thing about Triton is it's highly efficient, right? So all of the problems that I just described with actually doing low-level CUDA programming, they've worked out so that when you do stuff in Triton, it's more or less optimal. It's going to be better than most professional CUDA programmers can develop. It's going to be more optimal that way. And it integrates directly with things like PyTorch. So in fact, you can use torch tensors in, if you've ever done deep learning stuff with PyTorch, you can use torch tensors directly with Triton. And then there's QPy, which is this drop-in GPU accelerated replacement for NumPy, which is freaking insane. And I'll show you examples of that in a second. So PyCUDA, just real quick, you just pip install PyCUDA, and then you install a couple of the packages that are required. But this is how you define a kernel for that, right? Where it's basically you say, okay, I'm going to do vector addition. My vector addition kernel equals source module, and then I just give it a string. The string is really, as you can see, it's just the same CUDA kernel that I used in C. It's just now a string that we're passing via Python. And what PyCUDA does is it compiles it using the CUDA compiler as a function that it can now use, right? It can now launch to the GPU. So it's kind of cheesy, but it works. I have got an example here that I wrote that does this and I'll show you here in a second. In fact, maybe I can bring that up right now. Well, I'll bring that up at the end. Oh, I have it up on the screen, this screen. But that's okay. Let me switch back. Sorry, I didn't mean to derail the slideshow here. Okay. I'll show you in a minute. It's kind of clumsy with PowerPoint here, but basically everything else around this is just Python and Python data types and NumPy and things like that. So super easy to use. I should say that when it compiles your kernel, it will cache it, right? So every time you call it again, it doesn't have to compile it again. It's already cached it. And in fact, there's a mechanism you can use to actually compile it, store it to disk in a cache so that next time you invoke it from scratch, it's got that cached and you don't have to recompile any of your kernels. So yeah, some people will use that. Now, Triton, remember I talked about Triton. Remember, there's no direct CUDA programming. It abstracts everything away into just normal Python syntax, Python-like syntax. Dramatically simplifies the GPU programming. And the resulting CUDA kernels, like I said, are often more efficient than expert CUDA programmers can do. So if you go to triton-lang.org, that's their main site for their documentation. But let me kind of go through the code here, because this is actually pretty concise code for doing vector addition. It's got these decorators here. You can see this at triton.jit. This is basically what you need in order to put right above your kernel. Your kernel you define as what looks like just a Python function, right? It's basically just Python syntax. And yeah, let me think. Add kernel. Yeah, and then the I'm trying to remember the yeah, so this is all you do to define it, and then below is vector add. And so with a vector add, all you're doing, you're using torch tensors, right? To pass your stuff back and forth. That's why you included torch up here. It actually works off of torch tensors. But you define your grid. Remember, you talk your grid, you have to define your block size in your grid, just like you do in CUDA. And then I call this add kernel that passes all the parameters necessary to execute the kernel. So here, that's the function that does the actual add by calling that kernel. But here I just initialize a random vector of 10,000 values, make sure that it's on the CUDA device, on the GPU, just like you would do in Torch, right? It's a Torch call. So now you've used Torch to like create the random numbers on the CUDA device, on the GPU, and then you just call this vector add, which in turn calls the kernel. And so relatively straightforward. From everything I've read, this is generating a lot of excitement right now. I think there's a ton of people that are developing Triton and continuing to advance it. If I was going to be doing a lot of like powerful GPU stuff myself, I think the best route forward would probably be to use Triton to do that. Yeah. I don't know about JAX. Yeah. Okay. Is JAX a similar kind of concept for using Python and NVIDIA GPUs? Oh, okay. Oh, okay. Yeah. Yeah, I'm not familiar with JAX, but I've heard of it, but I don't know much about it. Okay, so I wanted to talk about CuPy. So this is like blows my mind, right? So CuPy is basically just a drop-in replacement for NumPy. So NumPy is like the most used module in Python, right? It gives you the certain data types and functions for doing math, for creating arrays and matrices, and it's incredibly powerful for just doing anything with math. But CuPy has all the same functions, but it will execute things on the GPU for you. And so remember all of that code that we went through before? Like you want to do a vector addition, assuming you have already defined your vectors. It's simply a matter of, assuming that these are vector types, this is all you have to do. And then this code will execute on the GPU, right? The same with sum reduction. So that complex thing that had the problem with warp divergence that I went through. If you use CuPy, it's literally just a matter of calling dot sum on your vector, and you'll get the sum. And it will do it in a way that's really optimal for your GPU. And matrix multiplication, dot products, all of that. So they have this on the website. They describe kind of the speed up that you get from using CuPy versus NumPy. And this speed up here is times. So on element wise kind of functions that you do in NumPy, you can experience up to 200 times faster performance by using CuPy. And it varies whether you're talking about big arrays or small arrays. The big arrays are in the dark purple and the small arrays are in the light blue. But there's always a speed up, and sometimes it's incredibly pronounced. So I'm going to be using CuPy a lot more going forward for sure. So one example that I wanted to give, and this is something, so our group does a lot of stuff with websites that do geostatistics sort of dynamically on large raster data. So like, say you have a geotiff of a large area of the landscape, and you want to find like an average or a mean or a min max of some channel within that geotip. Right now, the best we can seem to do is, in Python at least, is like to do multiprocessing, break it up into small things, assign different cores to that. And, rather than it taking a minute, which it used to, now we got it down to like 15 seconds. But now we can do it in like a couple milliseconds, right? And because you could take a giant raster at high resolution of, for example, the United States, where you're measuring some variable at high resolution, and it's trivial code in CuPy to find like the mean value of that entire giant raster, and do it on your web code. As long as you have a GPU, you can do this like super fast. And so it's going to open up, and I'm starting to think already about future web servers that our team buys, and they're definitely going to have GPUs so that we can make some of these functions utilize that hardware. So anyway, that's all I had. I'm happy to answer any questions anybody has. One thing, maybe I'll go and show now that this is over. I'll go ahead and show. I want to grab this. Okay. Let me show you. I wanted to show you the vector addition example in PyCUDA, because it was a little bit longer than I could really show in just on a PowerPoint slide. So again, we define our vector addition kernel here as a string. In this case, we give it this really long vector size, and we create basically just create a bunch of random values in those vectors just using NumPy. So everything else other than the kernel here is Python, right? And it's NumPy. You have to call this memory alloc function, but you're doing it in Python, not in C. And then there's functions for copying things from host to device and device to host, and then you basically invoke your kernel here. I set it up so that it would invoke the kernel in an infinite loop, so I could see how busy it made my GPU, and it seemed to do pretty well. Got it to about 70% utilization just by doing this vector addition over and over and over again as fast as possible on the GPU, but just adding random vectors. So anyway, I just wanted to show you that PyCUDA, I think can be really useful. I still think Triton is probably the way to go, but if you are interested and want to stay in a strictly pure Python environment, not Triton, which is Python-like, it's not really Python, it's Python-like, PyCUDA might be a good option. So I wanted to share that code. If you want to look at some of the other examples that I talked about today, I put that all on my GitHub repo, which is, you probably can't see that, but it's just github.com/Sheneman/CUDA. And all those examples are there, and they work. I will show you one last thing before I totally wrap up. You can also use CUDA to interrogate your GPU, to ask it like, what are you? What's your capabilities? That sort of thing. And so I have a little program here that does that in CUDA, right? So I include the CUDA runtime, and then I basically get I figure out how many GPUs I have on my device. And then for each of the devices, I go through and I print out the device number, name, the size of the warps, the maximum threads per streaming multiprocessor, and the total number of those streaming multiprocessors. And so, Yeah, and I actually do a little bit of math to figure out how many warps are per multiprocessor and the total potential warps. But yeah, you can do things like that as well to interrogate your GPU. And that's actually, if you're going to do low-level CUDA programming, that's important because you're going to want to know those details about the actual hardware you're about to run on, because you're going to need to modify, your CUDA code to deal with that. So okay, with that, I'm going to shut up. So thanks. Any questions or?
No questions so far in the chat,
Okay.
but feel free to ask.
Not really a question, just a comment. I want to look under the hood of that QPy just to see how it abstracts away like all of that memory detail and everything like that. That is really impressive.
Yeah, I'd like to see that too. I mean, it could very well be, the naive implementation of some of that stuff might not be as efficient as for example, you could get under, CUDA or Triton, but my guess is it seems really, really well developed. And so I suspect that they've got some pretty smart people working on that and have some pretty good implementations. Yeah. Yeah.
Is it possible for a trade all the trades?
To do what? Sorry?
Possible for a trade all of the another amount of trades. I don't know
If you have threads, you're talking about threads on a card. You're saying if you have trade threads across cards.
For example, if I have a code in a trade, this code in 2004, and I want to analyze this for loop. I call more trades.
Oh, you allocate more. So basically create kernels within kernels and like execute things in a branching way. Not that I know of, but it's possible. I'm not sure. I hadn't seen that before, but that's an interesting idea. Yeah. Yeah. There's all sorts of, speaking of for loops and things. I mean, one of the things that you can do, and this is true with regular code on CPUs too, but one of the things you can do to accelerate things is what they call loop unrolling, where instead of putting things in a loop, you actually explicitly like put them statement by statement, and sometimes that can help performance as well and prevent some problems. But yeah, as far as what you just described, I'm not sure. I don't think that's possible, but it might be.
Protections are there against like the data being appropriately formatted? Like if you just put in two vectors X and Y and they're different lengths, like what does it do? How does it react to that?
Yeah, that's a good question. I know that there's a lot of conditions under which a kernel will fail to launch. And so when you try to launch it, you'll get an error code back. I don't know, in the case that you just described where say for example, you have two vectors that are of different lengths that are allocated differently, but you try to, you're trying to add across them or something. That's a good question. Very likely that your program would just core down for crash. Normally in C, that's what would happen. You'd get some sort of memory access that's outside of your allocated memory, and it would just crash, which would be normal for a C program to do. And I suspect similar for a GPU, that your code would just come back with an error, is my guess. But
would it be like, I guess what I'm asking is, does the check happen like before everything's pushed over to the kernel, or does it fail on the kernel?
My guess is that it would happen at runtime. That kind of error would happen at runtime, and you would get some sort of memory exception that would cause your program to crash while it was running. Yeah. Yeah. With things like PyCUDA or CuPy, at least, that might be a different story, right? Because it's handled differently. But at the low level in CUDA, it's just like C code. It probably allow that you to try and then crash. So. Yeah. All right, thanks. I appreciate it.
Thank you so much, everyone.